Trigonometry can also come into play when we are describing complex numbers. And when we put it in what we are going to call trigonometric form, we are more able to do our operations such as multiplication, division, and taking roots easier with the complex numbers. To look at how this trigonometry applies, let's consider the ordered pair AB, XY, if we think of it that way, of the complex number z equal to a plus bi. If we look at our trigonometry, remember the sine of this theta right here is going to be opposite, which we're calling that the height value, our b, divided by the magnitude. Remember, this hypotenuse is going to be the magnitude of the complex number z, and the cosine is going to be a over the magnitude of z. Therefore, we can solve then for a and b and write those using the magnitude of z. What we can translate this into is our definition of complex numbers. We can define z equal to a plus bi, but we can say that z is equal to the magnitude of z times the cosine of theta, which is our a value, plus I times the magnitude of z sine of theta. Or you can think of it as the magnitude of z times the cosine of theta plus I sine of theta. Remember, z is that magnitude, and then we can define the tangent of theta is b over a. We define this angle theta as the argument of z, and that's a term you're going to hear a lot. So make sure you understand that term. It's nothing more than the angle with relation to the real axis. Once we have this information, we can relate the graphing of complex numbers to those polar coordinates we discussed previously. And note that that argument is going to have multiple values, but they will all be multiples of 2 pi. So let's practice writing complex numbers in trigonometric form. We have first here -1 plus I. The first thing we need to do, if z is -1 plus I, we need to know the magnitude of z. The magnitude of z is going to be -1 squared plus 1 squared. Again, that comes from a and b, which gives us a magnitude of the square root of 2. And we can determine theta because we know that the tangent, or the inverse tangent, is b over a. So the inverse tangent of -1 gives us an angle of 3 pi over 4. We know that's going to put us in the second quadrant. So if we want to graph that, we know it has an argument of 3 pi over 4. It's going to have a magnitude of the square root of 2. And then in that complex number in trigonometric form is going to be the magnitudes of z, which is the square root of 2, times the cosine of 3 pi over 4 plus I sine of 3 pi over 4. If we look at our second example there, where we have 3 minus 4i, again, we want to find the magnitude. The magnitude of z is going to be the square root of 3 squared plus the square root of -4 squared, which is going to give us the square root of 9 plus 16, or the square root of 25, which is 5. And we can write our complex number as 5 times the cosine of our argument plus I times the sine of our argument. And remember, the argument is going to come from the inverse tangent of b over a. So we have -4 over 3. We'd have to use a calculator for that, and we get an angle of -53.1. So we're going to take both the sine and the cosine of that angle, and this is our trigonometric form of the complex number. Please do note that this next example, we're going to write the complex number now in standard form. So we're going to go in the opposite direction. Notice this is our cosine is going to give us our A value and our B value. We know that the cosine of pi over 6, remember that pi over 6, we're looking at the angle 30, which was one of our often used angles. So we know that 2 times the cosine of pi over 6 plus I sine of pi over 6. We can get those values from our unit circle if you don't remember them. Becomes 2 times the square root of 3 over 2 plus I times 1 over 2, giving us a complex number when we distribute the 2 of square root of 3 plus I. It does require some calculus to prove, but there is an identity that we're going to use quite a bit that relates exponential functions with complex numbers as well. It's called Euler's formula, or Euler's formula, depending on how you wish to pronounce it. And what it tells us is that z is equal to the magnitude of z times the cosine of theta plus I sine of theta. But using this formula, we can rewrite this as the magnitude of z e to the I theta. This will come in handy in some future lessons, and we're going to talk about that in a future video.